because there was a street lamp, a gas, an old-fashioned, century ago, gas street lamp. And actually, that sounds dumb, but it's not so dumb if you think about it, because if the probability of finding it somewhere else, because there's no light, is 0, then it's just wasted effort, right? So even if you think it's, you dropped it somewhere else, but there might be a non-zero probability that you dropped it where you're looking at the moment, where there happens to be a street light. So, given that there is some light, there is some probability that you might find the key. So it's actually optimal to search where the light is because of the light, enabling you to actually see the key, right? Rather than somewhere else which you think the higher probability is where you actually dropped it, but 0 probability of finding it because there's no light. Okay? So by analogy, it's a bit of an old joke. By analogy, you got something similar here. That's why I brought up the joke, obviously. You can calculate it, right? That's the equivalent of the street lamp. If you can't calculate it, you can't really do anything with it. So much of applied mathematics in approximations, especially in teaching stuff, you teach with examples that you can actually calculate. Because if you can't calculate them, well, then it just becomes numeric. You're using a computer, and you don't really learn much from it unless you're really into numerical analysis. Okay. All right. Now that equation, which is proportional to alpha squared, just a constant. That's your parameter again, right? Alpha squared minus x squared. That takes the form. If you draw a graph of it, it's an inverted parabola, so it'll look like this. Now normally parabolas this way, but in an inverted parabola, like turned upside down, will look like that. So it'll have a maximum value. I hadn't thought about that before. Trying to get a minimum energy, right? So you're using a maximum valued eigenfunction. Food for thought. Yeah. You can think about that one. All right. Okay. So, but this inverted parabola, it's a sort of crude model of the Gaussian function. And the Gaussian function we had before was e to the minus alpha x squared. Right? Now, so this alpha proportional to alpha squared minus x squared is close to this. Right? If you expand this out a bit, you'll actually get something like this. So it's an approximation to an approximation, if you like. So we expect the expectation value coming from this second ansatz, the second trial solution, will be a bit worse, a bit more inaccurate than the first one. The first one ended up being perfect. Alright, so again I asked you to do it for homework. Calculate your expectation value for the Hamiltonian. I think this is already normalized. You better check for that. Check. This term here, I suspect, is your normalization constant here. But check for that. The textbook doesn't mention that, I think. Okay, so I think that is true, because when you find the expectation value for the Hamiltonian, you're using a normalized wave function, and this is the square of this term here. So it probably is already normalized. Okay, again, simple harmonic oscillator, right? So here's your Hamiltonian, no change. Here's your UT, twice, both real, so forget about conjugating, you don't need to do that. Calculate the integral, do it for homework as usual, second time, get you well practiced on how to do this. and show that this integral ends up being this, right? Okay, so that's your h bar expectation, this. Differentiate this with respect to alpha, and let it, that differential be 0. That will give you the minimum value for alpha. Now there is a there is no maximum value, because it could be infinite, right? Alpha just keeps going up and up. But there is a minimum value, and calculate what it is, and you'll get this here. Okay. Now this here is the expectation value for the energy. So once you've calculated what alpha is, plug it into here, and you'll get a value for the expectation value of the Hamiltonian. You'll get an estimate of what E naught is, right? And it works out. You all do this for homework, and you get about 0.6 h bar omega. So not bad, right? Because the perfect one, which here was 0.5 h bar omega. So it's about 20% off, right? It's not too bad. And just the second example, a different trial function will inevitably give you something worse, because you can't get better than perfect. Right? That was perfect. So okay, now that's the end of chapter 10. So a bit of space. So as usual, I don't know if I'm going to get this to work. Do something tricky. No. Well, I'll give you 3 more books, kind of add, foretaste of future courses. Now I've run out. I have run out of physics books to advertise, physics courses at undergrad level. Remember, I'll be another god. I may be a total of 2 years, possibly, just on the undergrad courses, because there are about a dozen or so, a bit more, and I've already advertised to you in the style I'm about to do. You're familiar with this if you've been following me closely on the 2 courses I've already done on undergrad group theory and undergrad quantum mechanics. So I've run out of physics courses, so now I will give you I'll give you an ad on 3 future undergrad level courses in mathematics, pure math. The first one is on complex variables. In other words, the calculus of complex numbers. So you're differentiating and integrating with complex numbers and complex functions. So I'll talk a bit more about that. I'm just giving you a quick overview at the moment. Second one is on topology, general topology. Often a synonym for general topology is point set. In other words, you're talking about the topology of a set of points. So point set topology or general topology. Now, modern, advanced, say PhD 2 level mathematical physics uses what? Lie theory, like Lie groups, Lie algebras, differential geometry, and topology, algebraic topology, stuff like that, cohomology, whatever. So you need, if you're going to be a modern mathematical physicist, as fluent in pure math as math physics, you're going to need a solid dose of topology. You're going to need to become a topologist, right? So this is like ground level This is ground zero of topology at undergrad level. And if you've never done topology before, you may find it a challenge, right? It involves a lot of analysis, lots of new concepts, topological concepts. Like very briefly, what is topology? Well, anything ending in ology in English just means study of, right? So it's some specialty, some academic specialty. Topos, Greek, Latin, probably Greek. I think it means shape or something. So study of shapes. More technically, specifically, topology is often defined as the study of those properties of a surface that remain unchanged when you squash the surface, when you deform the surface. Like for example, say you had a rubber donut, like a torus, solid torus, made of soft rubber, and you squash it and twist it and stretch it and whatever. So you're changing all the... imagine you had a felt tip pen with a fine tip, and you put dots. You marked the surface of the donut, the torus, the mathematical term for the same thing, like a rubber tire, the inflatable tire inside a car's wheel. That's a torus. So it's sort of this shape, like an American donut with a hole in the middle. Now, speaking of the hole, so you put all these dots on the surface of the torus, and when you squash and stretch and twist this donut, the distances between the dots and the angles between, say, 3 dots, so you have a dot here and a dot here and a dot here, and you draw a line maybe connecting these 2 dots and another line connecting these 2 dots with this dot here in common, then the angle here between these 2 lines, when you're twisting the rubber donut, those angles will change, the distances will change. So all your traditional geometry just goes out the window, right? It gets destroyed by the deformation of your rubber donut. But something stays the same. That's the hole, right? So the number of holes, 1, stays the same no matter how you deform the surface. Well, topology, often defined as studying the properties that remain unchanged. They do not vary, therefore they are, use the technical word, invariant, right? Doesn't change. So the topological properties are the study of invariant properties when you deform the surface. And if you have a family of these surfaces,